project milestone out, and we'll give you a deadline for when you have to form project groups. So if you haven't already, start talking with your peers about forming a group of 2 to 3 people. If you're having trouble finding a group, you can contact the TAs and the professors, and we'll kind of help you find a group. So more details on that to come. All right. So last time we talked about subgradients. This was the definition of a subgradient. We had a convex function, and if we knew it was differentiable, then we could use this lower bound that we get from convexity, that if I take the linear approximation around any point x, which is the right-hand side, f of x plus its gradient times transpose y minus x, and that's a lower bound for f of y. Right? That was just this picture. Differentiable convex function. If I take a linear approximation around any point x, it underestimates the function. Okay, subgradient is a generalization of this idea to a non-differentiable or possibly non-differentiable convex function. Just says that we call a vector g a subgradient of f at x if the following property holds. If I look at all y and look at f of y, it should be larger or equal to f of x plus g transpose y minus x. So here g is just playing the role of the gradient when the function is differentiable. So that's what we learned last time. We talked about some of its properties, that it always exists, essentially. If f is differentiable at a point x, then the subgradient is the gradient, and that's the only subgradient. And we also talked about how this also, the same definition works for non-convex functions, but they need not exist for non-convex functions. So you can talk about a subgradient of a non-convex function just fine, but it may not exist, depending on which function you're looking at. All right, so I'm going to skip through these examples because we went through them last time. Just to reiterate something that we learned last time, because this will be an important point that you see come up in this lecture and also over and over again. If we have the indicator function of a closed convex set, so we're given some function c, and we just write down the indicator function, which just gives us either 0 or infinity, depending on whether the point that we evaluated at, x, is in the set or not. Then subgradients of the indicator function are an important thing to know. And they're actually just, they're vectors of what's called the normal cone of the set C at the point x. So the normal cone of a set C, evaluated at a point x that's inside the set, is a set of all vectors g, such that when I look at g transpose, say, y, across all points y in the set, that's maximized at x. So g transpose x is bigger than or equal to g transpose y for all vectors y that are in the set. That just follows straight from the definition of a subgradient. For some vector g to be a subgradient of the indicator function, remember this is what we need to hold, that for all y, I get that the indicator function at y is bigger than or equal to the indicator function at x plus g transpose y minus x. Okay, and since we said x is in C, this is 0. So now let's look at two cases. If y is not in the set C, then the left-hand side here is infinite. So it actually holds for all g, right? And if y is in C, then the left-hand side is 0. So we're told that subgradients are points for which 0 is bigger than or equal to g transpose y minus x. Or in other words, g transpose x is bigger than or equal to g transpose y. Okay, so there are exactly those g's that satisfy this. The set of those g's is just called the normal cone. Okay, so here is a picture. Once you get a feel for what kind of the geometric characterization is for some of these things, it helps to remember them. So here's the set C. If I just pick some point x, and I ask for vectors that maximize the inner product with x among all points in the set, then they're vectors that are, that's why it's called a normal cone, because it's normal to the set at the point x. So this here is G. Okay, I've actually, in the picture, if this was 0, then what I'm drawing here is x plus G. But G is just this vector. Okay, yeah?
Are we saying that G is actually normalized always, or G can be any vector?
No, so G, that's a good question. So subgradients don't have any restriction on their norm. In this case, the normal cone is the set of, it's actually a ray that starts at 0 and extends out in this direction. So the way I've drawn it here, I've translated it by x. It starts here and extends out in this direction. So any such vector is in the normal cone. Okay, and if I'm at a point here, then you can convince yourself that actually the normal cone consists of all of these vectors in this picture. Yes?
I think with respect to this point, I think it's called a cone exactly because it's not normalized, but any multiple of it is still inside.
Right. So, I mean, maybe it's worth emphasizing that the normal cone is a cone. So if I take any point in the normal cone and I multiply it by a positive number, it's still in the normal cone. That's how we defined a cone. And we'll talk about cones in more detail later when we talk about duality. But we learned about them, I think.
Yeah, that's the definition for the cone.
Yeah.
I think again, geometrically, I think that's like when you say G transpose x minus y is greater than equal to 0. X minus y is a vector pointing from y to x. And so anything with positive dot product with those is, I think again, I mean, geometrically it's just anything with a positive dot product with all the vectors pointing towards that point.
Yeah, but so, I mean, you have to consider all y's, right? So that's why it's a little bit, I mean, one way to think about it is, as follows. So it's the set of all g's for which G transpose y minus x is bigger than or equal to 0 for all y. Say x minus y. Right, so if I look at any single point y, not sure how helpful this is going to be, but each one of these for a single point y, the set of g's that satisfies this is a half space. Right? It's the set of all g's for which G transpose x is bigger than or equal to G transpose y. Or I guess I could just keep it like this. For fixed y and x, that's a half space. So the normal cone is the intersection of all of these half spaces over all points y in the set. That ends up giving me, in some cases, something like this. In some cases, it just gives me a ray. So in this case, I take a point y. So let's suppose I choose this point y. And x minus y is the vector that points from y to x. Right, so I want to look at all vectors that have a positive inner product with this guy. So that's anything essentially in this half space to this side. And now I think about sweeping out all these half spaces over the entire set, and I intersect them all. And the only thing that remains are actually points that lie along this line. That's what gives me the normal cone. If you do the same kind of example over here, and you sweep over all half spaces, you'll see that actually I still retain everything inside this area. Okay, so there are various ways to look at it, but you know, I think once you get a feel for it, you can just kind of intuit what it should be and then check it formally. You can look at a picture and kind of intuit what the normal cone should be, and then check it formally. Okay, so this is kind of the important rules that we learn when we talk about subgradients. They're sometimes called subgradient calculus. They all follow right from the definition of subgradients, although some are more complicated than others. So the first is that if I have some function and I want to know the subgradients of a positive multiple of that function, a, for a fixed positive number a, they're just a times the subgradients of that function. A has to be positive because, well, think about it. We know that subgradients exist for convex functions and may not exist for non-convex functions. So if I took a to be negative, then this function inside, if f was convex, is concave. So the subgradients may not even exist if a was negative. Addition, if I just add two functions together, I can get their subgradients by adding together their subgradients. This is our version of the chain rule for subgradients. It has to do with linear functions. If I take f of ax plus b, where a is a matrix, and I call that G, the subgradients of G are just A transpose, the subgradients of f evaluated at ax plus b. This is a useful one to know. And now the next kind of two may appear to be somewhat technical, but they actually come in to be very useful. And if you, well, you're probably not concerned about the next homework, but when the next homework comes, you'll use one of these two to help you solve a problem. So I'd recommend paying attention, or at least coming back to these slides. If you have, yeah, question?
So you just said that there is no constraint on the size of the subgradient. So scaling doesn't make sense in that case because then it's just the subgradient of that anyway.
I said that's true for the normal cone. That's not true in general. So subgradients don't generically form a cone, right? Look at this function, for example. Right, so here a subgradient at 0 is anything between -1 and 1.
Anything and everything. So a times the scalar times equals 1 vector is the.
So what happens if I multiply? So this is a times a set. So multiply every element of the set by the number a. So think about what happens in this case. So the equivalent here would be taking the absolute value and looking at a times the absolute value of our function. So we'd still get that when x is not 0, the subgradient, instead of being the sign, it's a times the sign. So it's plus or minus a. And at 0, it's the interval minus a to a. That was a good question. But yeah, so just to be clear, subgradients don't always form a cone, but in the case of the indicator function of a set, they form a cone. Okay, so this one you can kind of believe from our example last time where we had the maximum of two functions. It's just the analog of this to a finite number of functions. If I have f, which is the maximum of m functions, fi of x, and I ask for the subgradients of f, then they're given according to this formula, which may look kind of technical, but it's actually very easy to remember. All I do is I look at the point x and I ask which fi's are active at x. So those are the set of all f's, the set of all i's for which fi of x equals f of x. That's what it means to be active, that that function achieves the maximum. And then I look at the subgradients of those functions. So each one of those is a set. And I take a union over all active functions, active fi's. And those are all subgradients. But we already know, we talked about last time, that subgradients form a convex set, a closed convex set. Right? So actually, not only these are subgradients, but the convex hull of all these points are the subgradients. So that's the subgradients of f at x. So if I have two functions, let's suppose I just have two functions, f1 of x and f2 of x, and I look at f of x equals their maximum as my function of interest. So this is a particular example. Let's even suppose that f1 and f2 are both differentiable. Then if I give you a point x such that f1 is bigger than f2, what are the subgradients of f in this case? Subgradient of f1, okay. And what's that in this case? It's just the gradient, yeah. So then that means that the subgradients of f at x are just the convex hull of one point, which is the gradient of f1, so that's just that same point. In other words, f is actually differentiable at that point, and that's its gradient. Okay, so the same thing holds for f2 of x bigger than f1 of x. How about x such that they're equal? What's the subgradient in that case? So how many terms are there in this union in that case? There's two. And each term in the union is what? It's just the gradient, right? Because they're differentiable. So it's the convex hull, just to read it off. Convex hull of the gradient of f1 of x union the set containing the gradient of f2 of x, which is just now a set with 2 points. So that's now, those give me all the subgradients of f of x. And what is that? What's that? It's a line segment, right. These are just 2 points. So this is just the line segment joining these 2 points. So if you go back to your slides, we had argued this kind of from first principles earlier for these two functions. But this is just checking that this definition gives us what we already know. Okay, so that one's handy. This one's even more handy, although it looks more complicated. It has a nice special form. Now let's suppose we have a function that's defined as the maximum over all. Instead of indices, I going from 1 to m, it'll be over all s in some set capital S. So this could be infinitely many things in this maximum. It could be uncountably many things in this maximum also. S is just a generic set of functions that are indexed by s, f subscript s of x. And I ask you, what are the subgradients of f if that's how it's defined? So it's really the exact same analogy here. It's just that we take all functions that are active, we take their subgradients, we take the union, but we know that the set of subgradients, or the subdifferential, has to be closed and convex. So we take the convex hull of that, and then we take the closure of that. And that almost gives us the subgradients. These are all subgradients of the function f, but we may have left some out, if this is my very kind of generic setup here. In most cases, essentially in all cases you'll encounter, this will be inequality. Okay, so under some pretty general regularity conditions on this set S and these functions f, we get an equals here, not a contains. So you can think of this as a contains for the purposes of the functions we'll encounter. Any questions about that? All right, so very important special case are norms. And you'll have to trust me at this point. We'll talk about this in more detail when we talk about duality. I feel like I said that a bunch of times. You can tell how important duality is now that we've already kind of hinted at it so many times in lectures. If I have the p norm of some for some value of p, then I can actually express that as the maximum over all points y, such that y has q norm less than or equal to 1 of the function y transpose x, where 1 over p plus 1 over q equals 1. So in this case, p and q are called, sometimes they're called complementary. But the important thing is that here the LP and the LQ norms are dual here. So I can always express for any p bigger than or equal to 1, the LP norm in terms of its dual norm like this. It's the maximum over all points that have q norm less than or equal to 1 of y transpose x. So let's just do this for p equals 2. If p equals 2, what does q have to be here? 2. So the L2 norm is self-dual. And I can always write the L2 norm of x as the maximum over all points y that have L2 norm less than or equal to 1 of y transpose x. Why is that? What would I take for y here that achieves this maximum? What do I take? Well, not necessarily, right? Because that doesn't have norm 1. I would take x over its norm, over its q norm, right? Or over its 2 norm in this case. That's it. OK, so now we know how to compute subgradients of norms of any type, just from this rule. Because this is f of x. And I've written it as the maximum over all y in this set, right? The set of all y such that has q norm less than or equal to 1 of y transpose x. And this is a case that you can believe me, we have those regularity conditions. So we get an equality in this rule up here. And we know that the subgradients of the LP norm are the set of all vectors y such that y has q norm less than or equal to 1 and y transpose x equals the maximum overall, I'll put z here, that I have q norm less than or equal to 1 of z transpose x. So they're just points that achieve this maximum. Another way of writing this much more succinctly is that the subgradients, I'll write it down here if I can squeeze it, are the argmax of over all y with q norm less than or equal to 1 of y transpose x. Okay, if you think about the argmax returning the set of maximizers, those are the subgradients. All right, so look for that on homework 2. That'll be useful. Any questions?
What kind of conditions are called regularity conditions?
So here, if S is compact and F is continuous with respect to S, then those are sufficient. So what does that mean? If S is closed and bounded, this is certainly a closed and bounded set, the set of all points that have q norm less than or equal to 1. And here the function is y transpose x. It's clearly continuous in y. Then we get equality. So those are regularity conditions, but the actual ones for equality are even weaker than that. Those are, you can remember those ones as ones that will give you the equality. OK, so why subgradients? Why are we bothering with this? It seems like kind of a mathematical tangent for what was a class so far about algorithms. But they're very important for 2 reasons. They're important, and probably more than these 2 reasons, but these are the 2 ones that I wanted to convey. So the first is convex analysis. So whenever you talk about characterizing optimality, you almost always run into subgradients unless everything you look at is differentiable. That really doesn't happen for very many problems. So there's a nice optimality characterization via subgradients that we'll see on the next slide. We won't talk about this in this class, but subgradients have a very important property called monotonicity. So they're an example of a monotone operator. And that enables you to do a bunch of stuff with non-differential optimization. They also possess a really nice relationship to duality, which is an important topic in its own right, that will enable us to do kind of a bunch of, to see things from a different perspective. Another reason, aside from those reasons I gave you, is the optimization reason, which is that if you can compute subgradients of a function, then you can minimize it. And that's true pretty much for any convex function. And that's what we'll be talking about after the break today, is a subgradient method. So it's a very general method. As long as you can compute subgradients, you can minimize the function. Not assuming differentiability, only assuming that it's convex. So here's the first thing I talked about, this optimality characterization. And this is a very simple statement, but it's very powerful. So let's suppose we have some function f, and we're not even assuming this function is convex. It's just a function. And I ask for you to find the minimum over all x of f of x. Then a point x star minimizes f. This is true, that x star is a minimizer, if and only if 0 is a subgradient of f evaluated at x star. So if I can check that 0 is a subgradient of f at a certain point, that certain point is the minimizer of that function. That's true for any function, convex or not. Why is that true? Well, it's a kind of embarrassingly simple proof. Remember, to be a subgradient means that the following is true. So G is a subgradient of f at x means that, according to the definition, f of y is bigger than or equal to f of x plus g transpose y minus x. And if g is 0, we just get f of y is bigger than or equal to f of x for all y. No, that's not only for convex functions, right? Because we define subgradients for any function. So this same definition I said works for any function. So this is the definition of a subgradient for any function f. Now, it may be the case that a non-convex function doesn't have subgradients at a certain point, and therefore those points cannot be minimizers.
So, but this y is to be in the vicinity of x, right? Like this is a local minimizer or global.
No, this is a statement about a global minimizer, right? Because subgradients, the way we characterize them is that this statement is true for all y. I'll even write in Rn if you want to be perfectly explicit.
I'm a little confused because assume that our function is differentiable. So subgradient is gradient.
Mm-hmm.
And we have a non-convex, so we have a local minima, and then we have a global minima too. So the gradient is 0 at the local minima.
Right. But the thing to remember is that for non-convex functions, gradients are not always subgradients. Remember, that was this example. This is one example of a non-convex function that's differentiable. This one's differentiable at 0, but that's not a subgradient. So it's an important thing to remember. It can be confusing. But are we all clear about this point? So for a convex function, its gradient, if it's differentiable, is its only subgradient. But for a non-convex function, it can be smooth but not have subgradients at points. This statement, though, although it appears trivial, it's a very powerful statement. It's an optimality characterization for any function. Global optimality. Now, whether it's useful for non-convex functions is debatable, because for a lot of non-convex functions, we can't compute subgradients. Either it's too difficult, or they don't have them at certain points. But it's a very useful statement to remember for convex functions. So it reduces to your usual, the usual thing you know in the differentiable case, which is that if f is differentiable at a point x, then saying that 0 is in the subgradient is just saying that its gradient is 0. Right? So it reduces to the usual rule. All right, so I wanted just now to take a brief tangent to tell you about why the normal cone comes into play. So this is unconstrained minimization, right? This is over all x in Rn. You might ask, what happens if I only look at points x in some set C? Right? Here, C could be a set. It could also be the set of all x such that I have a bunch of constraint functions satisfied as well. Right, this being the most generic form of the optimization problem we know. So then I can write this as the minimum over points x, not only in C, but all of Rn, of f of x plus the indicator function of C at x. Right, because that indicator function is going to be 0 when x is in the set C, and it's going to be infinite otherwise. So those are the same problems. It'll only allow me to look at points in the set C. And now this is our function. Let's call this function g of x. And let's just apply this rule up here to g of x. And it tells us that basically a point minimizes g of x if and only if. So this is, so we have x star is a minimizer if and only if 0 is in the subgradient of g at x star. Okay, what are subgradients of g? Well, we know from that subgradient calculus slide that they're just subgradients of f plus subgradients of the indicator function. So that's the same thing as having 0 is in the set of subgradients of f at x star plus the subgradients of the indicator function at x star. Remember, that was the normal cone of the set C at the point x star. So finally, if we can check that if minus g, I shouldn't use g since I use that for the function, I'll use v. If minus v is in the normal cone of C at x star for some subgradient of f, then we know we've minimized the problem. Okay, I should put x stars here. So if we can find a subgradient of f such that the negative subgradient is in the normal cone, then we have the minimizer. And for differentiable f, this just says that this is true if and only if the negative gradient is in the normal cone. Okay, so now we have a characterization of optimality for the most general form of problems we know. Again, this doesn't mean we can solve every problem because we can't always write down what the normal cone is. It could be very complicated. It could be complicated to write down subgradients of f, or sometimes maybe even the gradient of f. But at least we know mathematically what it means for something to be optimal. It means exactly this condition, which is a lot more explicit than this condition, right? Just saying that x star minimizes this. Okay, and we'll return to this kind of stuff later as well. So I'm going to go through two examples quickly of how we would compute subgradients. I guess actually that's my next example. This first example is using this optimality characterization to derive what's called a variational inequality. So here's one use of this optimality characterization. So let's suppose that our function now, yeah.
By the way, I think that that previous last condition can, I mean, intuitively, it can be made more obvious. That the last statement, I mean, that's basically saying that the gradient transpose x minus y is negative for all points.
Yeah, so that'll be what we see actually kind of here. But yeah, you're right. I mean, I can rewrite this, which you'll see kind of here in this next slide. But that's good foresight. All right, so let's just apply what we just learned to the function that I want to minimize y minus x. So you give me y. I want to minimize y minus x over all points x in some set C. So this is my f of x. And I'll actually rewrite this as the following, just to make it simpler. I'll square it and put a half in front. Doesn't change anything. Plus the indicator function of c at x. So this gives me the point x star that minimizes this, gives me the projection of y onto some convex set C.
Yeah, minimizing over the white space, not the second line.
Yeah, thank you. Thanks. That would be confusing. Okay, so here's my convex set. Here's some point y. I'm looking for the point in C that's closest to y. And maybe this guy, x star. It's found by solving this minimization problem. Okay, so this is f of x. So just from last time, this what we had just right here. X star is a minimizer if and only if this is true. That was for differentiable x. For differentiable f, our function is definitely differentiable. It's just the squared norm of y minus x. So what's its gradient? What's the gradient of this function? That should be hopefully not challenging. You guys should be able, maybe it was just that I said things quickly, but yeah, you should be able to compute the gradient of this function, x minus y. And the optimality condition is that x is optimal if and only if minus this quantity, so y minus x, is in the normal cone of c at x. So x is optimal if and only if this holds. Okay, and now let's just remember what the normal cone was. It's a set of all vectors such that when I take their inner product with x over all points in the set C, it's bigger than or equal to the inner product with any other point in the set C. So that means that y minus x transpose x is bigger than or equal to y minus x transpose u for all u and c. Or in other words, y minus x transpose x minus u is bigger than or equal to 0 for all u and c. Okay, it looks like I may have an unfortunate clash of notation with the slides, but you should be able to resolve that. So I'm just using x star in the slides where I'm using x here. I'll just make this x stars to keep that consistent. Okay. So let's draw a picture of what that means. I'll just redraw that convex set. I said that a point x star is the projection of y onto the convex set C if and only if this is true. So let's pick any other point u and c. And let's draw the vector x star minus u. That's this guy right here. I have to have the property that the line pointing from x star to y has a positive inner product with any of these vectors. Right? And that's true basically as long as those vectors that point from a point u to x lie below that line. So you can convince yourself that I can draw a line from any point here to the point x, and that's going to have a positive inner product with that vector that points from x star to y. Okay, and if x was not if the set C was not convex, then you can see this characterization is not going to make sense. Right? Why would that be the case? Because let's suppose suppose I had a set that looked like this, that kind of dipped back in on itself. Then even though x star might be closest to y, I could find some point u out here that when I form the vector u to x star, actually has a negative inner product with the vector from x star to y. Okay, but for convex sets, this is what it means to project on the convex set. For this to be true, this is called the variational inequality sometimes. We'll see this maybe again either on your homework, I haven't decided, or in the subgradient method lecture. But it's nothing more fancy than just taking what we know with subgradients and applying it to this particular function. Okay, so here's something that we could get right from the fact that x star is a minimizer if and only if the subgradient is 0. All right. The last thing we'll do before we take a break is we're going to derive this, use that subgradient optimality condition to derive this explicit solution to a pretty simple problem, but one that we'll be seeing a lot over and over again. So we didn't talk about this in the last lecture because we ran out of time, but we talked about kind of a noiseless version of this problem. Suppose we're in a regression setting and we have y and we have x and we want to regress y on x. So that would be the usual way to do it. That's just least squares. If we add a penalty to this, the L1 norm of beta, remember this is just the sum of the absolute components of beta, then we get what's called sometimes the Lasso problem in statistics. And it is a way of performing variable selection in this linear model. So it will set components of the solution to this problem. We'll call the solution beta hat, the argmin, to 0 exactly. We talked about the version of this where we minimized the L1 norm of beta subject to these two being equal. That was kind of like what I would call the noiseless version of this, where you think you actually observe y equals x beta, and you just want to find the one with the smallest L1 norm. Here we think we observe a noisy version of x beta, so y is probably close to x beta, some true x beta star. And we want to estimate that in a way that we get a sparse estimate. We use this estimator called the lasso. So we can't solve this problem explicitly. That's what makes it interesting to people who do optimization, but we can solve it explicitly when x is I, which means that we just want to find the minimizer of the following criterion. The vector beta that's closest to y plus lambda times the L1 norm of beta. So it's the vector beta that minimizes that criterion. And this will be something useful that we see come up again and again. If we know the solution to this, then we can, with some tricks, we can solve this problem in an iterative fashion by applying what we know about the solution to this problem. Is there a question? Or no? So I claim that the solution to this problem is given by, actually first before I write it down, let me ask you guys, is there a unique solution to this problem or not? Could there be many solutions to this problem? Or is there only one? Okay. That doesn't mean there's only a unique solution, right? Convex means that there's not local minima, but I can have a convex problem that doesn't have a unique solution. For example, here's a convex problem. Right? Any x minimizes that. Oops, you didn't see. Sorry, there you go. So a convex problem has a convex solution set. So the set of minimizers forms a convex set. Doesn't always mean that there's only one minimizer. There could be more than one. Another example is, let's just do least squares, right? Y minus x beta squared. What happens if x doesn't have full column rank? If I take duplicate columns in x, then I can take any, there's infinitely many solutions there, right? X has a null space. That's not just 0. So again, is this problem have a unique solution or not? It's convex, so it has a global optimum that we can find, presumably. But is it unique? I'm not sure we covered this. I thought we did.
I did cover it in the presentation.
So you covered in recitation. So a function, if the criterion is strictly convex, then it always has a unique minimizer. We learned what strictly convex was. That means that it's for example, if it's differentiable, then its second derivative is always strictly positive. Or just from the definition, right, a function f is strictly convex if we get strict inequality. So strict convexity means that f of alpha x plus 1 minus alpha y is strictly less than alpha f of x plus 1 minus alpha f of y. Yeah, that's true. But for the purposes of this point, this criterion is strictly convex. You can convince yourself of that. Why? Because the sum of two, if one function is strictly convex and the other is convex, then actually the whole thing is strictly convex. So it has a unique minimizer. So there's only one vector that minimizes this function. So keep that point in mind. I suppose if we didn't say that in a lecture, that's an important point. Unique solution if the criterion is strictly convex. So there's a unique solution because it's strictly convex. And I claim actually the following is the solution. That beta hat is given by taking y and soft thresholding it. Which means that every component of beta is given by yi minus lambda if yi happens to be bigger than lambda. It's given by 0 if yi is in the interval minus lambda to lambda. And it's given by yi plus lambda if yi is less than minus lambda. Okay, so here's what that function looks like. Right, if this is yi, then beta hat I is 0 between minus lambda and lambda. Otherwise, it's yi minus lambda for positive values of yi, or it's yi plus lambda for negative values of yi. So we set all the things to 0 that were less than lambda. Otherwise, we just shrink them. So how do we prove this? Well, we have a candidate for the solution. I told you it was a solution. So how would you prove now from what we've learned so far this is the solution to that problem? Yeah, okay. Sounds right. So I take the subgradient of this function. So what are the subgradients of my criterion? They are, so here's the criterion. I'll write it down one more time. What are the subgradients of that? Yeah, so I can take the subgradients of each thing, because that's one of the rules I know. I get beta minus y, that thing's differentiable. So subgradients of f of beta are the set containing beta minus y, or I'll just say elements of the subdifferentiable are beta minus y plus, I can take this out because it's positive, lambda times v, where v is a subgradient of the 1 norm. What are the subgradients of the 1 norm? We learned that also. Yeah, so here vi is equal to the sine of beta I if beta I is not 0. Otherwise, it's between minus 1 and 1. So if I take any such v and multiply it by lambda, and I add that to beta minus y, that gives me a subgradient of the criterion. So now I need to check that if I took beta as specified here, then I can get 0 here. So I want to check that I can make the subgradient of the entire criterion 0. If I can do that, I've minimized it. Everyone follow so far? Okay, so let's try sticking in beta equals soft thresholded version of y. And I want to make sure I can get 0. Okay, so let's just look at components of this individually. So I get, let's suppose that we'll go through some cases. yi is bigger than lambda. Then what's the ith component of beta, if it's the soft thresholded version of y? Then I get yi minus lambda minus yi plus lambda times vi. Right? And what was vi? Vi was equal to the sine of beta I if it's non-zero. And beta I here was yi minus lambda, which we know if yi is bigger than lambda, this is non-zero, so this thing is just 1. Right? So then this whole thing is just equal to 0. Okay, so we've done a good job. How about if yi is less than lambda? We'll go through the same calculation, and you'll find that we've made that component of the subgradient 0. And finally, how about if yi is equal to lambda? I'm sorry, if it's this should be less than minus lambda. And now I should have is in the interval between minus lambda and lambda. Then beta I is equal to 0. So beta I, so here I'll write down subgradient equals 0 minus yi plus lambda times vi. And vi can be anything in that interval. So what would I choose? Right, so those are all subgradients. And is there a subgradient now vi that would make that equal to 0? Right, so what if I take vi equals yi over lambda? That would certainly make that 0. And is that a legitimate subgradient of the L1 norm at the point beta I? Right, so subgradients are anything between minus 1 and 1. In this case, yi was between minus lambda and lambda, so this guy is certainly in the interval minus 1 and 1. So yes, that makes this thing 0. Okay, so we've just checked now that basically that's the solution. Any questions? All right, so that was longer than I had thought before we take a break. So let's take a break now. You guys can breathe for a minute. The slide we had on the optimality conditions for being a minimizer, and then we'll move on to the subgradient method per Aditya's suggestion earlier. So we had all all these steps were equivalent to for x to be a minimizer of some generic function f over a convex set C. And we said that we arrived here. For a differentiable function f, it's the same thing as the minus gradient being in the normal cone. And I added one more line just to write this out a little more explicitly. This means that the gradient transpose y minus x is bigger than or equal to 0. Y minus x star is bigger than or equal to 0 for all y in the set. So that you can just check that that agrees with what you know about the normal cone. And the interpretation here is that if I'm at x star and I'm thinking about moving to y, so I look at the vector from x star to y, and I look at the inner product of that vector with the gradient, then that's positive. So according to that local information, should I go in that direction? The answer is no, because the criterion is going to increase. Okay, so this is an optimality characterization for x star to be a minimizer. It's the same as this. But sometimes this might be easier to remember. That's how I remember it with the explanation I just gave.
For the definition of convexity, we get f of y greater than f of x plus a positive term.
Yeah, this also comes from,
Right.
yeah.
I'm saying that you can see that that's an optimality criterion because f of y is greater than f of x star for every y.
I didn't follow what you're saying.
So if you apply the definition of convexity, we get f of y is greater than or equal to f of x star plus a positive quantity.
Oh, yeah, sure.
And so you get f of y is larger than f of x star for all y in the set.
Right. So if we just imagine, if we know this is true, and we apply this definition of convexity, then we know that this tells us that f of y is bigger than or equal to f of x star plus this term, which we're told is positive. Okay, so various ways of looking at the same thing. Hopefully you haven't gotten confused in this discussion, but just remember, the basic thing to remember is that being a minimizer is the same as having 0 as a subgradient at that point. And then from that, you can derive all you want. OK, so we're going to start the subgradient method. I'm probably going to get through being able to tell you what it is and maybe how fast it is. But then we'll have to look at examples and such next time. So it's really not going to be surprising. Gradient descent we'd seen was just a way to minimize a convex differentiable function, and repeated these steps, right? We minimized x minus some step size times the gradient. It had a convergence rate of 1 over k. That's one thing that we actually proved. And what are its downsides? It had a bunch of upsides we talked about. Here are two of its downsides. It requires f to be differentiable. So this lecture, we're gonna well, I guess remains of this lecture, we're going to talk about how to get around that. And it can be slow to converge. Next lecture, we'll talk about that. Probably more like 2 lectures at the pace we're going. So subgradient method just replaces the gradient with a subgradient. It's completely analogous from that perspective. So if I want to minimize some function f, it's convex, not differentiable, then I repeat the following. I pick some initial point x naught, and then I look at subgradients of my function at my current guess. I pick one, call that g, and I just move in the direction of negative g. So it's really the same idea in this sense as gradient descent. Okay, but I'm allowed to pick any subgradient if there are more than one at my current guess. So one thing that's important to distinguish the two is that it's not necessarily a descent method. So if we run gradient descent, we always get a lower value of f at every iteration. That's not true with subgradient method. It could be the case that we actually get a higher value of our criterion value at the next iterate. So that's why we call it subgradient method and not subgradient descent, because it's not a descent method. So what we do, in addition to performing these iterations, is that we keep track of the best iterate we've seen among the points visited so far. So whenever we make a new update, we just keep track of the lowest value of the criterion we've achieved among the first k. And if our new one beats that, we call that our best one. Otherwise, we just keep as a record the point that has the best criterion value so far. Now, just to be clear, this doesn't mean that we don't move to a point if it doesn't make the criterion smaller. We still make a move to that point. So we still always update via this rule. But we keep track of the lowest criterion value visited so far. So if after 1,000 iterations somebody asks you for the solution, you just would have on record the point you visited that has the lowest criterion value.
Is that possible it goes into an infinite loop, like transposing between 3 points and like repeating the same value every time?
No. I mean, we're going to see that based on, well, we're going to choose the step size in certain ways. Most of our step size choices will not allow for that to happen. Because our step sizes are going to be decreasing, smaller and smaller. If it's a fixed step size, I don't know the answer to that. Maybe we could find a pathological case for which that was true. But we typically don't choose a fixed step size subgradient method. I'll tell you how to choose the step sizes in a second. And the choices that we make do not allow for that.
So I wonder whether this simplification is necessary for convergence or it just accelerates the convergence. I mean that if you don't have this if you don't take the mean, does it still converge or converge slower?
Another good question. So the proof that we have, actually there's a proof on the homework that you guys are supposed to be doing if you chose to do question 4, uses the xk best as to prove that it will converge. So that's the proof I'm familiar with. I don't know if it'll converge otherwise. It's another good question. I have to think about that. But given how little time we have, I think I should just keep going. Good questions. So what are the step size choices? You can choose a constant step size. We'll talk about the implications for that. Standard choice, however, is to choose diminishing step sizes. So step sizes that get smaller and smaller at every step. And this is probably the most common step size choice, which is step sizes that are square summable. So if I take the sum of tk squared from 1 to infinity, that's finite. But they're not summable. If I sum tk itself, it's infinite. So what's an example of a step size choice that will satisfy this? 1 over k, right. Okay, there are other options too for step size choices. This is not the only two. There's more complicated ones than this, but this is kind of the standard, this one right here. So the important difference to point out is that these are pre-specified. They're not adaptively computed like in gradient descent. There's no analogy to backtracking for subgradient method. So gradient descent, we can kind of adaptively choose the step size in order to make the best progress we can in every iteration. Subgradient method, we can't. We just fix them ahead of time, and we run the algorithm. And this is usually how we fix it, with this diminishing step size rule. So what are the things we know about subgradient method? If we assume that it's convex, not differentiable, right? Because that's why we're doing subgradient method, not gradient descent, and that the function itself is Lipschitz, not its gradient. It doesn't have a gradient in this case. But the function itself is Lipschitz with some constant, g, which means that, according to what we know about Lipschitz functions, f of x minus f of y is less than or equal to g times x minus y. Then, if we use a fixed step size, and we run the algorithm forever, then we'll get a point that's suboptimal. So it's not going to be equal to f of x star, but in the limit, it'll be less than or equal to f of x star plus g squared times t over 2. So the smaller the step size is, the less suboptimal it is. So already from this first result, you can kind of intuit that we want to make our step sizes smaller in the limit. Right? Because if they're not, if they just persist to some constant value, then all we can say is that it's suboptimal by an amount g squared times t over 2. However, if we take them to be diminishing, specifically if they are square summable but not summable, so like this choice, tk is 1 over k, then we can prove that in the limit we get a point that gives us the minimizer, or that gives us the minimum of our function f. Okay? So we're out of time pretty much. The next 2 slides, they just outline the steps that you're actually going to prove on homework 1. So how do you get these results? Well, you get them from what's called this basic inequality. And this is what you arrive at. And you're going to prove this on homework 1. You're also going to prove that if you have this basic inequality, and you just look at various choices of t, you get the results too. So if I stick in a constant for ti here, I get that first result as I let k go to infinity. If I stick in that other choice for ti, I get the convergent result as I let k go to infinity. So this is really the main workhorse for those theorems. And the last thing I'll point out before next time is that let's have a quick 60-second brainstorm session. What kind of functions are Lipschitz? So I require f to be Lipschitz. Intuitively, what kind of functions are Lipschitz, even in 1 dimension? Constant function, okay. Log. No, it's not going to be Lipschitz around 0, right? Yeah, so this is no. Piecewise constant functions, sure. Linear functions are Lipschitz, right? Piecewise linear. Oh, yes, thank you. This is not Lipschitz, right? Because I can make, right. So another example of a no is that I can make x and y arbitrarily close here, right? So L times x minus y is arbitrarily small, but the function value is not. The difference in the function values are not. Piecewise linear are. So now it appears like we've basically said that.
The pieces get, like the pieces could get steeper and steeper. So.
Like this, you mean?
Yeah.
Well, that might stop being a function at some point, right? If they get steep enough. Because then I wouldn't have a unique value at a unique point. Right? Like, do you know what I mean? Like if the pieces keep going like this, then at some point I won't have a unique value of the function.
No. It could just be a sequence that shrinks all the way.
Yeah, so it can be defined in an open interval, right?
Okay, all right, fine. So yeah, this could be some. You're right. This could be like I can make it kind of get shorter and shorter pieces all the way up until some point. I could define its domain to be open, so I don't include that point, so it's still a function. Yes, okay, so piecewise linear functions that have a lower bound on kind of the piece, the size of each piece. So it seems like we've basically determined that we can apply subgradient method to constant functions, linear functions, and piecewise linear functions. Is that it? Can we apply to any more functions? Sine and cosine. Okay. How about a quadratic? Well, I mean, this is not convex, so we probably don't want to consider that. Anyways. How about something like a quadratic? Or piecewise quadratic? Is there a question, or? Yeah, it's a good point. Did you have another?
Domain if we just limit or like have a band limited signal or like function, it will be Lipschitz.
I think you were saying the same thing, pretty much.
Sorry, I didn't hear it.
I think at least. So the important point to remember is that like gradient descent, we actually only need this to be Lipschitz over sublevel sets of our function. Or really, if we over a bounded set around x star. So if I look at some ball around x star of radius r, and I make sure that I start my algorithm in that ball, then all we need to do is make sure it's Lipschitz over this ball. So a lot of functions that may not look Lipschitz, like this quadratic, because its derivative keeps growing and growing in magnitude, or other possibly non-smooth functions that in portions maybe look like they're not Lipschitz in the limit, they'll be Lipschitz over this bounded set. Okay, so that's important to remember, just like our arguments for gradient descent, that we actually are solving a lot more problems than it may initially seem, because we only need to worry about Lipschitzness over bounded sets rather than over all of Rn. Okay, that's it, and I will see you guys on Thursday.